Okay, so let's look at the next set of 10 questions. So the first one is, for a copper metal, the conduction electron density is 8.45 into 10 to the power of 28 meter minus 3. The Fermi wave vector is, okay, so these are the options that are given to you. Now, how do you go about doing this in a very quick manner without having to actually calculate it? So what does the wave vector basically tell you? The wave vector, if you look at the magnitude of the wave vector, it's going to be the wave number, right? Wave number. So the wave number that you have here can be written as 1 over the wavelength. What is the unit of your wavelength? It's, let's say it's meters. The SI unit is meters. So the wave number has a unit of meter inverse. So which is the only option that has that particular unit? It would be this. So the answer is option B, but this is not the way I wanted to go because I think this basically has very less amount of physics in it. So the way I would want to know is I would want to know what it actually, I actually want to know what the formula is and all the physics behind it. Because you need to be able to do it for cases where the units are all very similar. What if all the units were similar? So you couldn't do it that fast, but this is a method to save time during the exam so that you can focus on other questions. Okay, so the Fermi wave vector for a three-dimensional system is what? Okay, so this is how your Fermi wave vector is. Note that it is for a three-dimensional system. Okay, I'm not talking about a one-dimensional system here. I'm talking about a three-dimensional system here. In that case, you have your Fermi wave vector, magnitude of your Fermi wave vector. There's no vector here. So the magnitude of your Fermi wave vector, Kf is equal to 3 pi square n. This is for a three-dimensional system. That's why you have the subscript 3. And what does n basically tell you about? It is the concentration of the electrons in a three-dimensional system. So this is very easy to calculate. You just need to know it's 3 pi square n 3 whole power 1 by 3. And what you have to do is you have to just substitute the value of the concentration of the electrons in a three-dimensional system that you had here. Okay, so they've given you the conduction electron density, which is basically the concentration of electrons that's there in your system. Okay, so what do? You substitute this and you get your 1.36 into 10 to the power of 10 meter minus 1. Now, there are a lot of other things that come up, not just the Fermi wave vector to calculate, but also other different things that come up, right? Like your Fermi energy, Fermi momentum, and so on. So, okay, so let's understand what your Fermi wave vector is actually. So it's the radius of the Fermi sphere, right? So how do you understand what the Fermi sphere is? Basically, when you start drawing your Fermi sphere, okay, so you've got, if you're looking at a three-dimensional system, you start drawing something like this, right? And what does that basically tell you? It tells you that, well, okay, inside this, let me just put a different color. So inside all of this, inside the Fermi sphere, I have occupied electronic states. And outside the Fermi sphere, you have unoccupied electronic states. Okay, so most people don't look into the physical significance of a Fermi sphere. They just study this, move on with the formula and the theory. So what you're supposed to understand is when you're talking about a Fermi sphere, you're talking about all occupied electronic states are inside this Fermi sphere. Unoccupied electronic states are outside this Fermi sphere. Okay, so it's basically like an abstract interface that defines the allowable energies of electrons in a solid. Okay, so now can the Fermi sphere always be spherical? No, it's not necessary that this Fermi sphere is spherical, and we will go on to I will go on to talk about that a little more in the coming slides. So the Fermi wave vector is the radius of the Fermi sphere. these quantities may not be well defined where the Fermi surface is non-spherical. So like I said before, the Fermi surface necessarily need not be spherical. Okay, it need not be a sphere. Okay, so let's look at this. Now, some of the parameters that I'm going to talk about are Fermi energy and Fermi momentum and so on, so that you can better understand how to deal with problems that come up when you have such terminologies that are asked for. So Fermi energy, the Fermi energy for a non-interacting ensemble of identical spin half fermions in a three-dimensional non-relativistic system is given by EF is equal to h cross square divided by 2m naught 3 pi square and divided by v whole power 2 by 3. Now this n by v here in your previous case was basically n. So you have an n by v, which is n. Okay, so that's your concentration per unit volume. Okay, so that we discussed before. And let's look at this. N is the number of particles. M naught is the rest mass of each fermion. V is the volume of the system. H is a reduced Planck's constant, and all those terminologies that you have. Now, if you notice in the question, be a little bit more careful when you look at the question so that you can understand this. Okay, it does say copper metal. Now, how are metals treated as Fermi gases? Okay, so let's go forth and look at this. Okay, so metals is a Fermi gas. Now, under the free electron model, the electrons in a metal can be considered to form a Fermi gas. So this is something that you might have learned in your third semester. You should have learned in your third semester because the chapter itself is about metals. Free electrons in metals is what I think I remember, if I remember it correctly, it should be free electrons in metals. So the number density n by v of conduction electrons in metals ranges approximately between 10 to the power of 28 and 10 to the power of 29 electrons per meter cube. Now, the reason I'm telling you this statistic or this particular this particular numeric is because then you can understand if you've gone wrong in your calculations, if you've gone wrong in your mistakes. Because if you have a metal that has been given to you, then the number density should be, if you're trying to calculate the number density and the, let's say the wave vector is given to you instead, and you want to calculate the number density. And if you're calculating it for a metal, then you can work it backwards. So you know that it's supposed to be around 10 to the power of 28 to around 10 to the power of 29 electrons per meter cube. So this is also the typical density of atoms in ordinary solid matter. Okay, so that should like if you know these numerics, it's well and good, because then you can solve your problems faster or easier. If the value of the concentration of electrons, say, is 10 to the power of 14 and so on, like let's say you have 4 options or so, 10 to the power of 28, 10 to the power of 14, 10 to the power of 3, and 10 to the power of 2, then you know that it's supposed to be this option, this particular option. So you don't even have to calculate your values. Now, the next thing is, what kind of energy does it produce? So it produces about 2 to 10 electron volts of energy. So if you've been asked to calculate the Fermi energy and you know that it's around this range, then it's going to be, again, one, it's going to be a check to know if you got the correct answer. 2, it's going to make, if you're running out of time, it's going to make you to sort your options easier if you're lucky that it's going to be in this particular range. Okay, so let's move on to Fermi temperature. So Fermi temperature is basically this Fermi energy divided by your Boltzmann constant. And so, okay, so the Fermi temperature is the temperature at which thermal effects are basically comparable to quantum effects that are associated with Fermi statistics. Now, the Fermi temperature for a metal is a couple of orders of magnitude above the room temperature. So again, 25 is basically the room temperature. So it's about a couple of orders more than the room temperature. So again, you got an estimate for those values. Remembering these estimates helps you solve the problems quicker or faster, and it's also a check to know if you got the correct answer. Okay, so next you have Fermi Momentum, which is again like the normal kind of momentum, except for you've got subscripts F. So PF is equal to root of 2 m naught EF. Fermi velocity, VF is equal to PF divided by m naught. And Fermi momentum again can be described in a manner like the de Broglie wavelength. Okay, so if you're looking at the de Broglie wavelength, it's lambda is equal to h by p. And similar to that, if you try to write this in terms of wave numbers, you get PF is equal to h cross KF. So now we've covered like almost all of the different Fermi quantities that are there. Okay, so another thing that I'd like to talk about is I told you that the Fermi sphere need not necessarily be spherical, even though it's typically called sphere. Okay, so what do you mean by, having a Fermi sphere? Basically means that the properties of the electrons that you're talking about in all directions from here, in all directions are going to be similar. Okay. So if it's perfectly spherical, then the properties of the electrons that you have, like the thermal properties, the optical properties, the magnetic properties, such and such, are going to be similar in all directions. If you do not have a sphere, there are cases, most of the time it's not a very perfect sphere. If the Fermi surface is not a sphere, then the properties of the electrons that you have, like the electric, optical, magnetic properties of the electrons, are going to be different. So just to show that it's going to be different, let me put it in different colors. So along this direction, it's going to be a different property. Along this direction, it's going to be a different property, and so on. Okay. So that's what is meant when you basically talk of your Fermi surface. Okay. So let's go to the next question. If the electron, I just want to make this point clear that we were trying to find out the Fermi wave vector in the previous question. All these points that I discussed are so that it can help in the other questions if so asked. Okay, so let's move on to this question. So if the electric field, okay, be careful. If the electric field developed in the presence of a temperature gradient, delta T, maintained at the ends of a metal rod under open circuit conditions, then the constant of proportionality in the equation E is equal to C gradient of T is what? Okay, so let's read it again. If the electric field E developed in the presence of a temperature gradient, so the electric field that you have here, the electric field that you have here is developed in the presence of a temperature gradient. So when you say there is an electric field that is developed, okay, when there is an electric field that is developed, there's obviously a potential difference that's going to be happening between the 2 points in the conductor. That's the typical understanding that you have, okay? So it could be a change, a gradient, or change in the voltage as well. So the fact that an electric field is developed indicates there's a change in potential. Okay, from point A to point B, there's a change in potential. So let's look at the several options. What is this particular coefficient that you have here? Okay, is it the Peltier coefficient, Joule coefficient, Seebeck coefficient, and thermal coefficient? So these are the different things that you have. I will explain each one like as we go along. Okay, so let's look at this. Okay, so the Peltier coefficient. The Peltier coefficient is basically the heat energy per electron per unit time carried to the junction. Okay, so Peltier coefficient and Peltier coefficient, it's pronounced Peltier. Peltier coefficient and the Seebeck coefficient. Okay, so these two effects that you have, the Peltier effect and the Seebeck effect, are basically the opposites of one another. Okay, so one involves creating a potential difference, and the other involves creating the temperature difference that you have. Okay. So let's look at this. Joule coefficient, it basically is a measure of change in temperature with volume. Okay. So we weren't talking about volume. What we were talking about is a change in temperature causing a change in potential. Okay. So let's look at the next one. So Seebeck coefficient. I want you to remember this term. Thermoelectric, thermoelectric power, thermoelectric sensitivity, or thermopower. One of the questions that we discussed in the last lecture, I think, involved talking about the Seebeck coefficient. And there, I think it was mentioned as the thermoelectric power or thermoelectric power. So that is basically Seebeck coefficient. So let's look at this. So the Seebeck coefficient of a material is a measure of the magnitude of induced thermoelectric voltage in response to a temperature difference across that material. So now do you get it? You had a temperature difference which caused thermoelectric voltage. Okay, so the last one that you have is something that you probably would have learned in PU a lot, the thermal coefficient. So basically, it's the coefficient of thermal expansion. You should probably know this coefficient of thermal expansion, which tells you how the size of an object changes with a change in temperature. Okay. So what is the answer for this? So the answer for this is basically your Seebeck coefficient, option C. Okay, so let's look at the next one. This is something that's there in PU chemistry. Okay, so 12th grade chemistry. We've basically talked about different stoichiometric defects. And in that particular, in your 12th grade chemistry. So what is your Frankel defect? So there are different kinds of stoichiometric defects. One of them is a Frankel defect, and the other one is a Schottky defect. So you have different ways in which these defects are described. So let me just, okay, so let's go over the options first. So a cationic vacancy, an anionic vacancy, a pair of cationic and anionic vacancy, a pair of cationic interstitial, and cationic vacancy. So let's look at this. Okay, so the Schottky defect. So basically what you have here is a cation and an anion. Okay, so this is this red things are your cations and the other green things are your anions. Okay, so the smaller ion here in this case, Schottky defect is basically seen when your cation is smaller than the anion. And Frankel defect, you could say that it's seen when both of them are comparable in size. Okay, so here in your Schottky defect, there is a missing anion, there is also a missing cation. But here in this case of a Frankel defect, your cation is basically been displaced to an interstitial site. Okay, so what is it? A pair of cation interstitial, because it has been displaced to an interstitial site, and a cation vacancy. So your Frankel defect, let me just go back. Yeah. Your Frankel defect is basically the cationic interstitial here and the anion that you have. So this is what you have here. Okay. So that's option what? That's option D. If you go back and look at this, that's option D that you have there. Okay, so let's just elaborate on this. Okay, so if you in case get different questions that come up. So your Frankel defect is basically shown by ionic solids. In this case, the smaller ion, usually the cation, is dislocated from the normal site to an interstitial site. It's called the dislocation defect. So if you're being asked instead of Frankel defect, if you're being asked dislocation defect, again, it's basically the same thing. And it does not change the density of the solid. So if you look at it, you basically don't have anything that's missing from the entirety of the solid. You just have something that has been displaced or dislocated. In your Schottky defect, you have things that are missing from the solid. So it alters the density of the solid. So here it's basically a vacancy defect in solids. Now to maintain your neutral, so basically the cations are positively charged, the anions are negatively charged. So what's going to happen? So in order to maintain your electrical neutrality that's there, you want to pull both of them out from there. Okay, so both of them are being pulled out. Now, this decreases the density of the substance, and there is basically, okay, so this is like a statistic. There's one Schottky defect for about 10 to the power of 16 ions that you have. Okay, so this basically happens in materials of similar size of cation and anion. Okay, I think I basically messed up a bit in the previous section where I said the cation and anion had to be same in Frankel defect, but it's in case of a Schottky defect. Okay, so yeah, so let's look at this. Okay, so when a DC voltage V is applied to across a superconductor, insulator, superconductor junction, what happens? So you have several different statements and you need to pick out the statements that are true. Now this question has a bit of an issue. Okay, the solution to this question I think is wrong. Okay, because there are, okay, so like we'll discuss that as we go along. So these are the different options that are given to you. Now, when a DC voltage V is applied across a superconductor, insulator, superconductor junction, what do you have here basically describing this kind of a junction that you have is called a Josephson junction. Josephson junction. Okay, and this is probably an experiment that you learned in one of the non-core papers that you had. Okay, there were a list of Nobel Prize experiments that we had to learn, and one of them was this. Okay, so this was okay, one of the experiments that people got a Nobel Prize for. So now let's look at this. The first thing is the Cooper pairs cross the barrier layer. So this is typical of any superconductor. But in this case of a Josephson junction, it basically has to cross the barrier layer. That's what is observed. An oscillating current of kilohertz frequency is produced. A photon of energy 2 eV is emitted or absorbed. A DC current is produced. A very precise value of E by H can be obtained. Okay, so now we need to, I think I should probably go into that a bit detailed. So I'm going to be explaining what Josephson effect and Josephson junctions are all about. Okay, so the Josephson effect is basically you have, let's say, a superconductor and you have insulator and you have a superconductor here. Okay, so one particular type of superconductor and another particular type of superconductor. Even though this barrier is there, what you do observe is that current flows through. Okay, so normally in a superconductor, what you do have is if it is basically at a different, at a particular critical temperature, then you do have a current that flows through it. Okay, but here in this case, in this junction, you basically have two different types of superconductors bridged by this insulator, and you do see that even though the insulator is not superconducting, the current passes through. Okay, so the phenomenon of supercurrent, a current that flows continuously without any voltage applied across a device known as Josephson junction, which consists of two or more superconductors coupled by a weak link. The weak link can consist of a thin insulating barrier. Okay, so there are different kinds of insulating barriers that you have here. So you have got a superconductor, insulator, superconductor junction. Okay, a tunnel junction, which I just talked about. You have another type of junction where you have a non-superconducting metal that's placed in between. Okay, and you have a superconductor here and you have a superconductor here. This is called the proximity junction. Okay, another thing that you have is a physical constriction. Okay, so you basically have a narrowing of the superconductor parts. Okay, so basically it's being constricted like this. Okay, between superconductor 1 and superconductor 2, or you have a micro bridge, or there's another case where you just have a point contact. Okay, so just a point contact, like this is the first superconductor and then it attaches like that. Okay, so that kind of thing is called a point contact. Now, in the DC Josephson effect, there are two types of Josephson effect. Let me just point that out to you. One of them is called the DC Josephson effect, and the other one is called the AC Josephson effect. I want to make it clear that applying a DC potential does not mean that it's a DC Josephson effect. I have seen a lot of people think that just because you apply a DC potential or a voltage, it does not make it a DC Josephson effect. The fact whether it's DC or AC is to do with the type of current that comes out of it. Okay, the fact to do whether it's DC or AC is the type of current that comes out from having this effect on. Okay, so in DC Josephson effect, a small constant current is applied, resulting in a constant supercurrent flowing through the barrier. Okay, the particles do not feel the presence of your tall tunneling barrier, and they flow with it through no driving potential. Now, Josephson current is basically a manifestation of the DC Josephson effect. There is another situation, like I told you, where the current actually oscillates with very high frequency, and that is called as AC Josephson effect. So the output current is what we're looking at to say if it's DC or AC. Josephson junctions basically have lower critical current. So what is the advantage of using this over normal superconductors? It's that the critical current is lower as compared to that of the normal superconductors that you have, like the bulk superconductors that you're talking about. So there were two predictions that Josephson made. The first prediction was that there is a relationship between the current and the difference in phase. So when we're talking about two different types of superconductors separated by this barrier, this superconductor, okay, this superconductor, so these are basically condensates, right? So this particular thing has a phase, let's say phi 1, and this particular superconductor has a phase, say phi 2. So the current relationship, the current that flows through is given by the difference in the phase between these two superconductors that you have. Okay, so phi 1 is a phase of the condensate wave function of S1, okay, superconductor 1, and then you had phi 2, which is a phase of condensate wave function S2. Okay, so the second prediction that you have here is that the derivative of the change in phase is given by 2 EV divided by H cross. Okay, and this, there is a problem, a homework that comes up. You have to try and calculate the frequency that is associated with a particular value of the potential, which is very easy to do. Okay, so let's go on to do this. So let's look at the AC Josephson effect first. Now, let's consider a constant DC voltage driving the particular junction. So you're applying a constant V voltage, and the phase difference delta phi is equal to 2 EVT divided by H cross. That's very easy to do. You take this differential equation that you have and you integrate it. So then you end up getting the particular value of phase that you require. So you have delta T is equal to 2 EVT divided by H cross. On putting this first approximation, putting this particular thing in the first approximation or the first prediction, we have the current that we require. So I is equal to IC sine 2 EVT divided by H cross. Okay, so this, let's say it's of this form, IC is equal to sine omega T. Omega is equal to 2 EV divided by H cross. That means F is equal to H cross is what? H cross is basically H by 2 pi. Omega is equal to 2 pi F. So F is equal to 2 EV divided by H. Okay, H. Okay, so now let's look at this. The current basically fluctuates between plus IC and minus IC with the frequency given by 2 EV divided by H cross. Okay, so now when we're looking at a DC Josephson effect, it's basically a direct current that's crossing on the insulator in the absence of any electromagnetic field, no external electromagnetic field. And this happens basically due to tunneling. So it is not always possible to keep the voltage across the junction a constant. So it's better to try and keep the current constant. And these are the associated formulas that you have. So if the current has to be kept constant, what do you have here? If the current has to be kept constant, then this thing that you have here, okay, there is no potential here. So in that case, your phase becomes a constant. Okay. So the phase becomes a constant and the bias voltage has to be 0. Because from the first prediction you had what? I is equal to IC sine delta phi, right? So if the phase is a constant, then the current here has to be, the current is kept a constant, and the phase is a constant. If the phase is a constant, then the bias voltage is 0. If the electric potential difference across the junction is V, these are some certain points that I have kind of like noted down so that it's easier to understand the question options. If the electric potential difference across the junction is V, then the energy difference between the two superconductors is 2 eV, since each Cooper pair has twice the charge of one electron. Okay, so just note that what we're talking about is the energy difference between the two superconductors being 2 eV because of Cooper pairs, because these Cooper pairs, electrons go together in twos, right? The next point that I want you to do, this is like a homework, very simple one. You can do it probably even like in hardly a minute. So like I said before, omega is equal to 2 eV divided by h cross. So the F is equal to 2 eV divided by h. So that's your oscillation frequency that's given. Now I want you to show that the DC voltage of 10 microvolt causes an oscillation frequency about 5 gigahertz. Okay. So if you do this, then you get the order of the oscillation frequency in your head. Okay. So just a second. Yeah, if you do this, you get the order of the oscillation frequency in your head. So once you get that done, then it will be easier to kind of like understand what are the different things that are associated with this Josephson effect. Okay, what are the different points? Now, the other one point I'll have to show you is like there's a lot of research being done on this. Basically, if you look at H and E, they are fundamental constants, right? So the AC Josephson effect has been used in precision determinations of the value of H by E. So I think this is to do with the fact that Josephson effect can help detect very small magnetic fields, like the magnetic fields of your brain, of your heart, and so on. So it's used in squids and a lot of other devices that can help you in in a lot of healthcare devices like scanning and stuff like that. Okay, so let's move on to the next. Okay, yeah, before that, I have to go back and tell you about the different things. So let's go back and look at the question that we have. Okay. So now, when a DC voltage V is applied across a superconductor insulator superconductor junction, what happens? So the first thing that you have to understand is that we're talking about AC Josephson effect. Josephson effect. Okay. So how do we know that? You're applying a DC voltage. If you're talking about DC Josephson effect, it's basically just due to tunneling. So there's no applied potential there. The next thing that we have to look at is which one of these are correct. So Cooper pairs cross the barrier layer. That is true, right? Cooper pairs do cross the barrier layer. So that's a tick. An oscillating current of kilohertz frequency is produced. Now, this again is a homework so that I can reiterate this point. It's of the order of gigahertz. Okay, it does depend on the applied voltage, of course, but it is of the order of gigahertz. Okay, so you need to calculate that and like do that homework and understand that particular point there. So this is wrong. Okay, so a photon of energy 2 eV is emitted or absorbed. That was not the case. Let me just point that out to you again. Okay, so let's go to the last slide. Okay, so remember, if the electric potential difference across the junction is V. Then the energy difference between the two superconductors is 2 eV, since each Cooper pair has twice the charge of one electron. But that does not mean there's a photon of that much energy going to come out from that. Okay. So, yeah. Okay. So it does not mean that a photon of energy 2 eV is emitted or absorbed. Okay. Between that particular difference. So this is wrong. Okay. A DC current is produced. No. It's AC Josephson effect. So an AC current is produced. So this is wrong. And a very precise value of E by H can be obtained, which I showed you in the last point. And why are they important? These are fundamental constants. So knowing the correct value of these fundamental constants is very essential. And therefore, you can use these techniques to understand that. So this is correct. Now, which of the points here match here? Okay, so which of the points that you have here are matching with this? None of them basically match because only two options are correct. Okay, so they've given it as option D. Okay, this is what is given, but I think that is wrong because nobody objected it. They just left it like that. So this is not the correct option. Look at the question and understand it instead of like directly going on to the options, because otherwise there's no point in trying to do this, right? So this is the correct option and this is the correct option. 1 and 5 are correct. The rest of them is wrong. Okay. So let's go to the next question. Okay, so this is quite simple. Okay, the relation between resistivity of a metal at high temperature T is what? Okay, there is a bit of specificities that you need to note down here. You're talking about a metal at high temperature. Okay, so everybody knows it's linear. It's something that we've all learned since like, I don't know when, like probably in middle school physics, right? So let's look into some of the things that are there. So the resistivity of material depends upon the temperature. The relation between the temperature and the resistivity is given by rho is equal to rho naught, 1 plus alpha T minus T naught, where rho and rho naught are the resistivities of the temperatures at T and T naught, and alpha is the temperature coefficient of resistivity. Okay, so therefore rho is proportional to the temperature. Fine. But let's look at this. Okay, so let's look at the different cases that there are. In metals, the resistivity increases with temperature and alpha is positive. In alloys, the resistivity is large, but have weak temperature dependence. Alloy has residual resistivity even at absolute zero, while a pure metal has negligibly small resistivity at absolute zero. Okay, so there is some amount of residual resistivity for alloys. So what the three categories that we're looking at are metals, alloys, and one more. Let's look at that. Semiconductors. So the resistivity here decreases with increasing temperature and alpha is negative. So let's look at this. This guy is your conductor. This guy is the alloy that we talked about. And if you look at this, you still have some amount of residual resistivity. And this is semiconductor that we talked about. So alpha here is negative, alpha is positive, alpha is positive. Okay, so now the next thing I want you to note is the dependence of resistivity at a low temperature for conductors and at a high temperature for conductors. High temperature, it's quite linear. We all know that. But let's look at it more closely. So look at this. So this is at low temperatures. This is the entire thing. Okay, so this is low. This is high. Okay, and at low temperatures, at this particular point, it's kind of like flattening out. Okay, so this is again, look at it. Both of them are for conductors. One is for the whole range of temperature and the other one is just for low temperatures. So you can't say that the resistivity is linear for metals at low temperatures. Okay, so it's not linear always. It's only linear when the temperature is high. Okay, so the resistivity was the temperature curve for your conductor. Okay, so you notice the linear rise in resistivity with increasing temperature at all but very low temperatures, at all but very low temperatures. And the next thing that you have is resistivity, is the temperature for a typical conductor at very low temperatures. So you notice that the curve flattens out and approaches non-zero resistance as T tends to 0. Okay, so now in this case, so this you would have to do a bit of reference. Okay, there is some amount of reference in this question. Also, you need to look into one of the references that I've given in this, basically. So this is a huge derivation to calculate the bandwidth. Okay, I will give you an idea of how to do it, but this itself would be like a 1 or 2 hour talk. Okay, so I cannot go like entirely into detail, and this is not something that has been taught before. Like it's not been done in your MSc, or I think probably the elective courses would have, but I highly doubt it. Okay. So in the tight binding approximation for a simple cubic lattice, the bandwidth is 15 gamma, 12 gamma, 9 gamma, and 6 gamma. Okay. So how do you understand this? Before I go into the postulates, I want to give you a basic idea of how we try to attack this. Okay. So why are we using an approximation here in this case? We're using an approximation because we cannot find out how it is for an actual system. Now, the thing that we're talking about here is a simple cubic lattice, right? We're talking about a simple cubic lattice. We are talking about, let's say, a crystal, okay? And we want to know how to understand the crystal. So in your earlier quantum mechanics courses, what you usually did was you understood, you found out, let's say, the Hamiltonian, or you found out the eigenfunctions for basic systems like free particle in a potential well, infinitely deep potential well, square well, and let's say simple harmonic oscillator potential. Okay, so if you notice all this, all these are potentials. Okay, so you're constraining something in a potential. Now, what we're doing in this case is that we understand that free electrons, are not really found, right? Unless, of course, you try to generate one. Free electrons are not really found in nature. So free electrons, or electrons, let's say, are typically bound. They are bound to a particular potential. And electrons are basically bound to an atom. Okay, so when you try and say that electrons are bound to an atom, you can represent it as a potential. Okay, so let's just say this can be represented as a potential. Now, in your crystal, what happens? In your crystal, you basically bring a lot of atoms together, okay, in a particular sort of arrangement. And all of these can be represented as potentials, okay? Each of them can be represented as potentials. Now, these atoms are basically arranged in a crystal. So what you do have is you start seeing electrons in periodic potentials, okay? So they kind of like merge together and they create something like this. So each of these can be written in terms of a particular wave function, and you can try to find that out, okay? But you know for a particular system, okay? So the system you know, this is the system you know. And then there is this system that you don't know entirely, okay? System you do not know. So what your idea is to take the system that you do not know, express it in terms of a system that you know, plus a perturbation. And I'm hoping that probably because of the lockdown, your second semester did not go well. But I'm still hoping that you did learn a bit of perturbation theory. I mean, like you did learn it properly, because a lot of the systems that are talked about further on are systems which have a Hamiltonian, okay, the Hamiltonian or the actual Hamiltonian plus, okay, which is equal to the Hamiltonian of a museum piece. Okay, so what do I mean by museum piece? It's basically kept in the museum for you to look at. Everything about it is already known. So you can use that particular thing and understand something that is not exactly that. Okay, so you can put a perturbation and you can try and formulate it. So what is happening in the crystal that you want to understand? Okay, so let's come back to the simple cubic lattice or the crystal that you want to understand. You do not know everything about the system. Okay, some information is better than no information at all. Okay, so here you do not know anything about the system. So you try and express it in terms of a system that you do know plus the perturbation. So you need to start applying perturbation theory here, and that's how the derivation goes. Okay. So this is an extensive derivation. Probably if you're really curious about it, you can try and look into it and read it up. But if not, this is the best I can go to with such short amount of time. Okay, so these are the different postulates that there are in this tight binding approximation. So apart from this tight binding approximation, you do have weak binding approximations. Okay, so that's like an entire chapter in this book that I'm going to mention. Okay, so let's look at the first postulate that's there. The energy eigenvalues and eigenfunctions are known for an isolated atom. Like I told you, all of these are known for an isolated atom. You utilize this plus the perturbation theory that you know, and then you try to apply and try to get a result from it. The next thing that you have is when the atoms are brought together to form a solid, the atoms remain sufficiently apart from one another so that the electron can be assigned to a particular atomic site, so that you can make up this periodic arrangement of atoms in your crystal. The next thing that you have is the periodic potential of the lattice, V of R, is approximated by a superposition of atomic potentials. Okay, and the last one that you have is perturbation theory can be used to treat the difference between the actual potential and the atomic potential. Okay, the closeness, you really never truly approach, you really never truly get the answer or the energies that you require, but you can get really close to it. Okay, so yeah, so this is what's mentioned after the derivation in that particular textbook that I looked at. So for a simple cubic lattice in the tight binding approximation, we obtain a bandwidth of 12 gamma. Okay, so the energies that they've got is about 12 gamma. Now for the detailed derivation, okay, so this is the book that's there. Okay, so it involves using a lot of perturbation theory. Your solid state properties, this is the textbook's name. Chapter is chapter 3. Why is this very faint? Okay. Oh God. Okay. I don't know why it's very faint. Okay. Just a second. Okay. So this is basically chapter 3, weak and tight binding approximations. And in the tight binding approximation section is where you will find this particular derivation for your simple cubic lattice. And it's not just for simple cubic lattice, it's for all the other different types of lattices that you have. Okay. So what is the option? It's option B, 12 gamma that you have here. Okay. So next question, liquid helium does not exhibit which of the following? Fountain effect, lambda transition, thermomechanical effect, phoromechanical effect. So, okay, so I think we did talk about lambda transition when we discussed the 2013 paper. Okay, and we talked about this in lecture number 6. I'll probably put a link of that once I upload this into YouTube in the description. Okay, so this is fountain effect. This is lambda transition. This is thermomechanical effect and photomechanical effect. Okay, so let's just understand each of these. Okay, so you know that we did talk about helium a lot, I think, in the previous papers. Okay, so it is the superfluid helium is a state of matter that exists at low temperatures and has a lot of remarkable properties. One of them is the fountain effect or the thermomechanical effect. Okay, so if you heat a jet of helium, it converts heat into mechanical motion. You're basically having a machine here with no moving parts. It's like a heat engine. Okay, but it's only working below 2 Kelvin. And okay, so the fountain effect is the thermomechanical effect, and I will elaborate this a little bit more on the next slide. What I want you to look at lecture 6 for this on a detailed discussion. So what would we talk about there? We talk about lambda transition, the phase change to superfluidity, which liquid helium undergoes at 2.2 Kelvin. It's so named because of the shape of the specific heat Cp versus temperature graph, which looks like a lambda. Okay, so it resembles lambda, and that's why it's called a lambda transition. And they also call 2.2 K as the lambda point. Okay, so if you're below the lambda point, then you have like superfluid helium. Okay, so yeah, this is your lambda, which I showed you there in the previous lecture. Okay, so now coming to the fountain effect, basically what is happening here is, okay, so initially this is not the state. Initially how it looks is, initially what's happening is you have this kind of a tube which is there, and there's a bulb here at the bottom. Okay, so there's a bulb here and it's filled with some kind of a amorphous material. Okay, and there's a cotton plug here. So basically what happens when you put this into the liquid is that it's just flat. Okay, so in a normal liquid, what's supposed to happen is no matter what you do, you're supposed to be getting this is flat. Okay, now what they do is they irradiate this particular portion, okay, which is black in color, this particular portion with a light. Okay, and because of that, there's being heat generated here, and due to the heat that's generated here, all the superfluid part, okay, superfluid part of helium 2, superfluid part of helium 2 goes in through this and comes out like this. Whoa. Okay. Goes in through like this and comes out like that. Okay. So this is basically your fountain effect. Okay. So let me just make it clear. This is basically a hot point. Okay. Hot. This part is basically cold. And there is fluid that flows from here going here. Something that's going from the cold region to the hot region, which is kind of against convention, right? This is not how things flow. It basically flows from the hot to the cold and not from the cold to the hot. Okay, so that's very peculiar. That's why this is very peculiar. And superfluid exhibits such strange properties that are there. So the heat that's being pumped on here, okay, the temperature difference that you cause here is making this superfluid, this thermal effect, thermal thing, convert to mechanical energy, and therefore it's being pumped up like this. Okay, so let's go back to the different options that you have. So now what do you know? You know that the fountain effect that you have here is the same as the thermomechanical effect. Okay, these two are the same thing. Lambda transition we talked about already, and photomechanical effect is what? Okay, so I think there's a really nice thing, interesting stuff to be talking about here. Okay, your photomechanical effect. So what happens in a photomechanical effect? So it is a change in the shape of the material when exposed to light. Okay. And a lot of people use this. I don't know if you know, there's this surgery called the LASIK surgery. And basically, it is like to correct your myopia or hypermetropia, stop wearing glasses, basically. So basically, what they do is they irradiate laser into your eye. Okay. And then they try to create acoustic waves. Okay, so acoustic waves is basically the mechanical part. So you're using photons to create acoustic waves. Okay, you're using lasers to create acoustic waves and then basically break up certain materials. So this is used in the LASIK surgery. It's also used in removing. Okay, so a lot of people have permanent tattoos. It's used to remove these permanent tattoos that you have. Okay, if you made a mistake and you really don't want that tattoo anymore, how do you remove that? You break those particles up. Okay, so these particles that are used to create tattoos on your body are quite large. Okay, that's why they stay there under your skin. Now, if you break them up into travelable, okay, things that can be passed through your veins, obviously, they can be removed. Okay, so it's used in tattoo removal. It's also used in this particular thing that I told about, your LASIK surgery. So what happens there is basically the cornea of your eye is basically kind of, what happens is basically there are small defects in your cornea. Okay, that's how you have this issue with trying to see far or near. So what they do is they incident laser light on top of that. Okay, the incident laser light and all of these this gets basically corrected. Okay, and how do they correct them? They change the refractive index. So these acoustic waves, refractive index. So these acoustic waves basically create a change in your refractive index of the lens that you have in your eye. Now, you can also see that, I don't know if you've noticed this, but earlier days, the glasses that you have used to be very thick. Okay, so people used to wear very thick glasses or spectacles. Okay, very, very weird way to draw that. Anyway, so it used to be very thick. Okay, and that was because people did not exploit this property of refractive index. So when your refractive index goes higher, is increasing, the thickness of glass reduces. And if you go to stores nowadays, if you go to stores where they sell your glasses, they actually price more for glasses with refractive index of higher thickness because then it's thinner. Okay, so these are more expensive compared to the other ones. So if you look at these old movies or something, I think you can see that the thickness of the glass of the actors are very, very thick or something like that. Probably no, nowadays nobody wears them because people have actually exploited this property of changing the refractive index to make the glass thin. Okay, so that was a long discussion. Let's move on to the next one. Okay, so this one basically it's to deal with this one is basically to deal with liquid crystal displays. Okay, so there are different types of liquid crystals. I think I am not sure if you learned this because I took a different elective and I'm not sure if it's there for the students who took the condensed matter elective. Okay, so liquid crystal cells are basically used in your LCD display, which is very famous nowadays. So which are the different types of cells that they use? Okay, so you'll find really interesting applications for this. And some of the things that you did not know where liquid crystals are actually liquid crystals. Okay, now apart from the phases of matter that you have, like solids, liquids, and gases, there are also intermediate phases called liquid crystals. So at certain temperatures, some materials that you have become liquid crystalline. Okay. And these intermediate phases, which are liquid crystals, they flow like a liquid. Okay. But they have some kind of optical properties of a solid. So it's like an intermediate phase between your solid and liquid. Due to the ordered arrangement of their molecules. So if you look at them, they're basically like very, very straight shaped. Okay, they flow in a very linear way. They flow in this way, unlike a liquid, which is basically flowing in all sorts of different directions. They flow in a very, very straight fashion. Okay, so they flow like a liquid, but they have the properties of a solid. Okay, so one type is called the Lyotropic liquid crystalline phases, which are found in living systems and your cell membranes and stuff. There are other things which depend on the temperature. So there's cholesteric, thematic, and pneumatic. Okay, so the first type is basically used in mood rings and things like that. So I don't know if you go shopping on Brigade Road, I think this is really fancy to get a mood ring, which basically changes the color based on the temperature of your body. Okay, once you wear it, based on the temperature of the body, and they say it's a mood ring rather than, if you have a fever, it basically doesn't tell your mood. Okay, so the thermometers and some displays. Okay, so this type is used in this. Now, the spectic liquid crystals are basically like, they form layers like soap, and the pneumatic are basically the ones that are used in your cell phones and calculators and TVs and such. So now this exactly wasn't really useful when they found it out. This itself isn't very useful, but it's very useful if you twist it. Okay, so the twisted pneumatic effect, TN effect, was a main technology breakthrough that made your LCDs practical. So yeah, unlike your earlier displays, this did not require current to flow for operation. That was the main difference between this ordinary pneumatic and twisted pneumatic. And they used very low operating voltages. So then suddenly this became the most in thing. So most of the LCDs that you see today are made of twisted pneumatic. Okay, so let's look at okay, so what is the option that we have to check? The option that we have to check is option C, twisted pneumatic. Okay, so yeah, this is very easy. This is something that you all know actually. Hopefully, I'm hoping. Okay, so which of the following are probable to be captured by the nucleus? Is it K shell electrons, L shell electrons, M shell electrons, or your outermost shell electrons? It's very obvious. The ones that are closer to the nucleus are going to require less energy to pull itself and fall into the nucleus. Okay, so it's the K shell, option A. It's commonly a K shell electron which is captured. And what is this basically called as? This process is your electron capture. Okay, and it's a form of radioactivity. We will be talking about a lot of problems in nuclear physics coming forth. So I would probably, there are a couple of points and similarities and differences that I'd like to talk about this and beta decay. So yeah, I will talk about in the coming questions because the session is quite getting too long. Next one that we have is a parent nucleus. Okay, yeah. So the next point here is basically a parent nucleus captures one of its orbital electrons and emits a neutrino. The easiest one to catch and the most common one to catch is your K shell because it's closer to the nucleus and the energy required is much lesser compared to the outer shell electrons. The next one that we have is binding energy per nucleon is maximum for the nucleus. Which type of nucleus is it maximum for? And there are different types listed to you. I'm hoping you might have done this practical, and I'm not certain if you would have. There is this chart experiment, chart calculation. I don't even feel like calling it an experiment. Okay, so there is this thing that you do if you're a nuclear elective student, you would have done it. If you're from Bangalore University, there is this calculation that you have to do where you have to use a semi-empirical model to calculate the binding energy per nucleon. And you have to plot it also. So there's a whole graph that you need to do. So the easiest way to do this is not to actually calculate the binding energy per nucleon, but rather look at the chart and remember which goes where. And also some certain facts about these metals that you have. Okay, so metals are certain elements that you have, not metals. Okay, so this is how your binding energy per nucleon, the chart looks. Okay, so average binding energy per nucleon in this direction, and here you have number of nucleons in the nucleus in this direction. So let's say which were the elements. So Fe, lead is somewhere here, molybdenum 101. So this is molybdenum 98. There is a 101 somewhere here, and I think helium was the one. Helium 2. Let's just go back and look at it. Yeah, helium 4. So it's not this. Rather it is this. Okay, so helium 4, lead, molybdenum, lead. Yeah, so those are the 4 things that were there. Now, one of the peculiar things about iron 56 is that it is abundantly available. And whenever you have something that's abundantly available, that's the most stable element there is. So they've actually marked this region as the region of greatest stability. Okay, so what was the question again? Let's go back. The binding energy per nucleon is maximum for the nucleus. It is iron 56. Okay. So yeah, so the binding energy per nucleon increases with atomic number and its maximum for iron. After that, it basically decreases. So the reason why iron 56 is the highest binding energy per nucleon of any element, and this explains why there's so much of it in the universe. So I think that's a really interesting fact that you can remember, so that you know that the binding energy per nucleon is highest for the isotope iron 56.